Swayam Prabha. Digital India. Educated India.
Okay, dear all, so as I propose that I will again start some tutorial. So let's see, in this class I will show you again some problems. As I said, this is not just a discussion of the questions and answer. This is just kind of the problem that I am throwing you and try to answer. Then you can think independently some new problem. You can try to design some new concept for biosensor design. That is the main goal to teach this all the tutorials. So that's why today's main concept that I will cover. Let's show you some basic tutorials, the problems, and then try to solve it in the different way. So whatever I taught until now, let's summarize everything in a single slide so that you can solve these basic issues. Let's see. So first questions for today. Describe some signal amplification strategies to obtain the higher signal to background ratio for disease diagnosis. Say, so when this kind of questions may come, how you will start to solve this? So here I mentioned describe some signal amplification strategies, right? So just think the signal amplification strategies I taught you. Mainly, please try to think here. I taught here redox cycling, redox cycling amplification, amplifications. So describe some signal amplifications means you can start some EC means electrochemical, right? Or maybe you can start ECC. ECC means electrochemical, chemical redox cycle. So this kind of redox cycles may help you to amplify the signal. So you solve the first part. Now here they mention to obtain higher signal to background ratio. So signal to background that I already told you in the last tutorials also. Like all the strategies you have to keep in mind while you will design. So the main goal to give this problem is design a sensor device, but that is very generic. That is very generic thing, not like very specific. So here that's why I don't mention any specific disease, just for disease, any kind of disease. Like this way, please try to think fast. Then you can try to design some very specific biosensors. Okay, so those things just try to remember. Now here, see, in this problem, this is again some generic concept, so that whatever you learn, let's bring all together here in this problem. Suppose this is also can be a one project for you, who are the students who are thinking for your higher study. You want to go to another university for your internship, or maybe you want to go for maybe 1 year project. Like you may think about like a small project, like how to design a lab on a chip for cancer detection. Means if you go for the whole optimization of the lab on a chip, it can be a PhD. All of your 4 to 5 years you may take. But you may, because it is very interdisciplinary, design a lab on a chip, then its optimizations, then cancer detections. But also it can be like just go for a specific cancer, specific cancer, like prostate specific antigen. Suppose, for example, I choose. Then this is the biology part, prostate specific antigen, and here is the your engineering part. Engineering part is the design a lab on a chip. So this chip design. So first what you will do, let's make your chip right here. So on chip, it should be useful for point of care. That definitely you should keep in mind if you want to, because in this course is design, the main concept is for point of care. So that's why I am teaching you such a way. So it should have a inlet, right? Inlet means where you will drop your sample, and outlet, there will be outlet. Outlet means excess solutions may come out. Okay, and there is no need many steps, sample handling, sample purifications, sample amplifications, those things you don't need. But definitely we need that will be automatic, everything on your chip, it will be automatic. What layman will do, they just drop the sample and they will wait, and they wanted to see the value that I said, some digital value they wanted to see, like the glucometer. What we are doing in the glucometer, just we prick the finger, 1 drop blood, then we take this blood on a chip, then just you can see after few seconds you will see the digital value on your detector skin. Something like this lab on a chip concept, right? So such a way you can design your project. So inlet means here, so you can definitely you have to integrate this one with the microfluidics. Why we need microfluidics? Because you can handle easily. Maybe in this inlet will be your sample, right? You need another inlet where you can add some reagent. Maybe you will be provided a tube that will contain some basic reagent, right? For your amplifications of the signal that I taught you, know, like some chemicals, that some very basic chemicals, and that you can provide. So one thing you can ask me, sir, if we provide this chemical, maybe they may not be stable for longer time, because once I prepare and then you are when you commercialize this, maybe this solution you have to keep it for a longer time. That time you may be destabilized, it may not show the very stable data day to day. So what you have to do, maybe you can make some solutions with a stabilizer so that it should be stable, or you can give some very basic buffer solutions with some reagent you can keep on the chip in a lyophilized condition, so that they will not be unstable. That you have to keep in mind. All the details again I will show you, how to store all the reagent and how to go for packaging of your final device. So that is very important part. If you not follow the packaging part, maybe if you keep in the air, maybe it can be oxidized, maybe somehow your reagent can be damaged, right? Packaging is a very important part. That you just try to think here. Maybe after this tutorial I will show you again very details way how to go for the packaging. That is very important for the stability. Without good packaging, you cannot commercialize your device. So here your chemical, here your sample, you may add some more inlet also based on your requirement, and there may be a serpentine like this way you can design your microfluidics. Why? Because you need proper mixing of the sample. Maybe see here, maybe you have some reagent, here you are adding the sample, but you may think you may add one by ones also. Maybe sometime first add the sample, then wait for a few minutes, so the sample may come to your sensor. Maybe here you will be your sensor, your working electrode, your reference electrode, your counter electrode. So and it will be connected to it through your microfluidics. Then your microfluidics channel will be here in the outlet. So excess solution will go out from this outlet. Okay, so your solutions, your reagent may come like this way, then it will come to your working electrode, then your target, if you have the cancer target like prostate specific antigen, so it will bind. So on your working electrode, your prostate specific antibody, that is antibody 1, will be here, right? And now if you have the prostate specific antigen, then it will bind. Then another part, maybe you can give like a secondary antibody that conjugate with the methylene blue, right? That I taught you already, that it will come, then methylene blue will be bind, then it will form the sandwich, right? Then another way you can send some chemical, but I'm saying very simple way, but you need a optimization that you can go for a project, that I'm saying, like how long you want to, like when you mix the sample, everything, how you want to start, like first maybe your sample, then it will bind, then this, there is some incubation time that you have to think, there is a design of this microfluidics, this serpentine structure that you have to optimize, right? Your nature of the substrate of the microfluidics, that also you have to optimize, and you have to check which one is the best, size of the microfluidic channels, everything, lots of factor. That is called optimization of device. That is very important part. It may take some time. That's something. It may be your PhD whole project also, if you go for a very systematic way. If you want to develop really a good point of care device and you want to commercialize it, then definitely you have to go very systematic way. Then this design of the sensor. When here is a sensor, main electrochemical sensor part. Your electrochemical sensor are here. So your working electrode, reference or counter electrode. Then here see your connector. So here you can connect with a small portable potentiostat. So here you can design a portable potentiostat. Portable potentiostat, just like glucometer potentiostat you have seen, right? Something like this. So your potentiostat. So maybe here will be your connector. So this will be connected here. This will be connected here. Then here you can see your digital value, or else what you can do, you can transfer this data via wirelessly. Wirelessly you can transfer this data, that is IoT enabled. IoT enabled a device you can make. That's what I'm saying. This whole part is the engineering part you can make. So IoT enabled means via Bluetooth you can transfer this data to your smartphone, right? You don't need any extra detector. So on your smartphone you can see the data. So how? Maybe on your smartphone there will be app like PSA detection app. Just turn it on and via Bluetooth it will transfer the data and it will connect to your mobile phone and you will see. So such a way we can develop a smartphone integrated nanobio sensor. This is the engineering part that you can do. This whole things it may take longer time also. And biological part, that is the things we can handle, that is the sensor part, right? Like working electrode, counter electrode, reference electrode, right? That here means how you want to modify this sensor working electrode, and then you want to modify your antibody. Then which concentrations of primary antibody you are immobilizing on the working electrode, right? That concentration you may need to optimize. Because sometimes signal to background ratio is very much close to this antibody concentrations on the surface. If you use very low amount of the antibody on the surface, then easily your surface can be saturated. Why? Suppose you are making a calibration curve, right? So maybe few picogram, nanogram, then your sensor can be saturated. But if you can really optimize your surface with antibody, then you can go further, nano to maybe microgram also. It will not be easily saturated. So your detection range of your sensor will be very high, right? Maybe femto, pico, nano, micro you can detect. But if your optimization not done properly, maybe within nanogram it will be saturated. So that's why this part also you have to take care. Then again the concentrations of your reagent. So many, for if you want to use ECC redox cycling, there is many chemicals, but I will prefer, if you want to really commercialize and you want to make very simple cheap, I will prefer let's go for very simple reactions, not like very complex. ECC reaction means very little bit complex, right? There is lots of chemical there. Let's go for first very simple reactions. For that you have to go for some review. Like if you go review like prostate specific antigen, you want to detect what is the clinical range, actual clinical range in human body. If you see, if you go the like normal patients to like who are the critical stage, what is the range of the PSA? You can check, it will start from picogram per ml to, then again it will go to slowly higher concentration, maybe nanogram, something like this. Picogram per ml means you don't need very ultra sensitive biosensor. I mean, you don't need actually really to use the electrochemical chemical redox cycling. Maybe just simple redox cycling like EC redox cycling, just simple redox cycling can help you to detect the picogram level. I mean, so if you can detect like the healthy range to the like who are in the critical stage in the patient in this PSA range, then that's fine. Then no need to make them more complicated, right? No need to make the complications on in the reaction side. So don't use the ECC. Let's try EC only. Like this way you can design. So, and for the EC you need maybe like 2 chemicals. Let's try to optimize their concentrations, right? That part also you have to take care of. Okay, then you may need washings, you may need some here pump like valve you may need. That also you may think like manually you want to just inject it, or there will be some automatic that just press on, just push this button, then automatically it will start. Something like this you can design. I'm just giving the concept, you may think. Now let's come the again some, this is, don't think this is a problem, this is kind of a like a small project I am teaching you. How can you develop multiplex diagnostic microsystem for rapid quantification? Means last slide we developed a lab on a chip, that is for single detection, right? Single detection just like PSA, but we can go for multiple analyte. Like you may need to detect like cardiac troponin I, like some another like this kind of biomarker related for the heart attack, or myoglobin. So myoglobin or cardiac troponin I, so they are related to the this for the heart attack. So in the like when age like more than like 50, and nowadays you may see the younger age also this kind of level may come, and we are facing the different cancer or heart attack. But if we can design a device like here your whole sensor part, one sensor can detect prostate specific antigen, another cardiac troponin I, another myoglobin. So when the age become 50 or more than 50, so we may keep this kind of small device in home, and regularly we can, regular means not like every day means with months or after few months, like every 6 months, like we can check this level that this kind of disease may come like slowly, not suddenly, but if we check it regularly, maybe we can take the precaution, we can take the doctor's advice, and definitely we can save the patient life. This kind of device definitely will be helpful for society, that's why. And for that, nobody will come to doctors every time to check my prostate specific level, troponin level or MB level. If you have something in your home, maybe it can go for the your self checking, and you can do this kind of some data that you can predict, you can take some your own decisions. That is really useful, so that we can minimize this kind of death. So this is the motivation. So same way, let's design a lab on a chip for multiplex diagnosis. So one for PSA, one for troponin I, one for myoglobin. Two way you can make. One, they are the working electrode. Here you have to immobilize your specific antibody for PSA here, troponin I here, MB here. One way, just working electrode separately, common counter, common reference. Or another way you can design, another way is that maybe you can make like separate a working counter reference, working counter reference, here working, like this way also you can generate. So then you need many connector here, that's all. And same way, like you will have inlet here, maybe here you will have one outlet, here inlet, here also inlet, and you can design what like I taught you in the last slide. Then what you will do, like, so in this case you may need like separate inlet. You can, I may say, as it is the multiplex, you don't know that all are present or not together. So let's use only one single sample, and then this sample may come, it will go through this whole surface, right? It will go through the whole surface. Then there will be the outlet, and then it will come here excess solutions, and you will have like others like reagent, or if you may need some buffer, that you can try, right? Here you may need some buffer. Those are the things. And you may need here serpentine structure, because to mixing of the all the things like your reagents, your sample, that you can design. That like similar like I taught you last slide. Like this way you can make a very innovative and important lab on a chip. But just try to remember, there is a two part, as I told in the last slide also. One is your engineering part, that is the design, and another is your biological part. In the biological part case, you have to properly review like which marker you want to go for the multiplex development, right? Like based on the current scenario, maybe there is in the winter time, then you are facing like fever, right? So you may develop a device cause for this fever like dengue, or right now COVID. So dengue, COVID, malaria, maybe you can combine together, right? Or this is because of this like viral fever or some bacterial fever, that also you can make, right? Well, you don't know. Sometimes if you, because of viral fever, you are giving the antibiotics. So what happened? Nothing, and your body will become a antibiotic resistance, right? So in the future your body become resistance, and if you add the antibiotic, it will not work. So you actually it is more dangerous. That's why you may decide, I mean doctor also can check in his chamber, that his or her chamber, that yes, this is for viral, then don't prescribe him the antibiotic, or it is antibiotics, don't go for the viral treatment. Something like this you can design some lab on a chip. See, that's why this tutorial I am also giving the concept, so that you can think about this kind of problem and design something new idea. Okay, so now this, see, so here sensor part ready. One is the your engineering part, that is the design of the sensor, and another is the biological part, that selections of the target. You selected all the target. Now if you want to make the more handy, more smart a device, what you will do? On the back side of this chip, as I taught you already, the PCB based biosensor, right? That concept now you can bring here. What you will do, on the top of the PCB you just design your all the multiplex sensor, and the back side of the PCB you can integrate your electronic part. That is the utility of the printed circuit board. You are using one part sensor and another part the electronic, because easily electronic small part you can integrate with the PCB. So there you can make a small potentiostat itself, potentiostat, because you have to apply some input, right? Some potential, like for the oxidation scale like 0.3 volt you want to apply. So this potentiostat may help to apply the potential, and all the like electrochemical technique that you want to apply here, maybe cyclic voltammetry, maybe impedance, maybe chronocoulometry, amperometry, whatever, those programming you can set here, and that you can make a app on your smartphone, and in that app you can connect this one wirelessly through your smartphone and your device. So your device will be connected through your smartphone wirelessly via Bluetooth. So it is IoT enabled biosensor. So that what happened? So this chip backside you have all the electronic part, and via Bluetooth, by controlling your app, once you start, then your chip will get the signal, then let's run. Then run means it will start apply the 0.3 volt automatically. Then how much current it is generating? That much current equivalent to how much target concentration for like target 1, target 2, target 3, everything will transfer to your smartphone. And here you will get the 3 data, T1, T2, T3, 3 data you will get. Then that data also can be stored to the cloud, so that doctors also can access this data. Means in any emergency case, doctors also can give you immediate advice to you. Yes, you need maybe some treatment immediately. So it is kind of, that's why IoT enabled smart device is really important in this current time. This technique you are applying on the smartphone, this hold the device. That's why it is very important. This technique you should use. Yes, that problem that I told you in the last slide, like describe the importance of printed circuit board for the development of the lab on a chip. That I taught you. No, let's use PCB for biosensor development. Why you need the PCB? Because you can easily integrate your electronic part on your biosensor. You can make a IoT enabled smart biosensor for POC, point of care testing, POC, that help you. Okay, that's why you need the printed circuit board. And another thing, the PCB that you know already, I taught last class when I taught the PCB, easily you can fabricate. We have very good fabrication technology. That's why you need the PCB. Okay, so that's you have to keep in mind. So that I taught you, that how to develop the new concept. Please try to remember these all the concepts. That's why this, as I told you at the very beginning introduction class, this class is not only for your exam pass. So you will get all the techniques, all the concept for your future study also. For like you can start your own startup, your own career you can start like this way. That's why this tutorial is very equally important, and easily you can pass your exam. Because if you have all this concept, this same questions may come in the exam also. So let's go through all the tutorial. I may start some more tutorial in the next few classes. Then I will start again some new topic. Okay, thank you students. Thank you.